Okay. I'm going to talk about inscribing a rectangle within a graph. Now, the problem you have, you're inscribing a rectangle in a graph of a polynomial that opens downward and lies above the x-axis. I'm going to do something by analogy, or just show you how you would inscribe a rectangle in the reciprocal square, the graph of the reciprocal square function. So we start, here is your inscribed rectangle, but let's construct it step by step so we understand how it was constructed, and then by analogy be able to construct it for the given parabola in the homework problem. Okay, so again, here's your graph of the reciprocal square function. It's not a very accurate graph. I didn't get the symmetry right, but you get the idea. So we pick a point on the x-axis. We call its coordinate, surprisingly, x. Okay, so we can pick a coordinate. We can pick a point anywhere on the x-axis, even on the opposite side. But that coordinate is going to be called x, and x is a variable. So we could look at how the area of the rectangle varies as we vary the value of x. So, to draw a picture, to get a sketch, we just pick some value, we call it x. So, here are the steps. Okay, we're inscribing a rectangle between the x-axis and the graph. That's what we call this. First step, we pick a point on the x-axis. Okay, well, there's a point in the x-axis, and we call it x. And let's put that in there. We call its coordinate x. So I say call the coordinate x. And this has nothing to do with this picture. This picture is a picture of the way the inscribed rectangle would look for the inverted parabola of the assigned problem. So I'm going to kind of rub that out, pretend it isn't there. It doesn't have anything to do with this. It was put in there late when I was trying to draw the parallels between this situation and that situation after doing all this. Okay, so again, our graph, we pick a point on the x-axis and we call its coordinate x. So the 1 here refers to the fact that this is step 1. We got the point x. Somebody, I think, interpreted this 1 as the coordinate of this point, and that looks about right. So maybe a little confusion, but that just refers to step 1. We pick a point and call it x. Then we find the point directly above this on the graph. Okay, well, the point directly above it on the graph, we go directly above it, and there's the graph, and there's the point 2. Okay, so we got a circle 2 with an arrow to this to indicate that's what we do in the second step. Then we form the horizontal side at this point. Form a horizontal side at this point. What's that mean? Well, horizontal's in this way. Horizontal side, implicitly side of our rectangle. So here it is. There's a horizontal side of the rectangle. It's got to have its vertices, its upper vertices, on the graph of the function. The lower vertices are on the x-axis. So, if this is the upper vertex corresponding to this value of x, then we got to have this vertex over here. It's going to have the same y value as this one because this line is horizontal. Okay, so we form that side at this point, and then we form a vertical side from this point. So we have a vertical side from this point implicitly down to the x-axis because that's where the next point has to be. Okay, so there it is. And then the fourth side, of course, is along the x-axis. The first side would have been the side from here to here. So now we've got our rectangle, and we've got to figure out what the area of that rectangle is in terms of x. Okay, well, to find the area, we better find the dimensions. Now, it took us a while to work through this because these are not, it's a learned skill being able to look at a graph and answer the kind of questions you got to answer here. So I broke it down a little bit. What's the length of the first vertical side? That would be this side. What's the length of this side? Well, the vertical side, the length is just equal to the y-coordinate here, because we're going from the x-axis up to this point. So the question is, what's the y-coordinate at this point? And once we have the y-coordinate, then we know we're going from y equals 0 up to this y-coordinate. Okay, well, the point on the graph here is xy, but y equals 1 over x squared. That's the function. So the point is xy with y equal 1 over x squared. So the point is x 1 over x squared. Those are the coordinates of the point. And if you want to think about it, this point where the x coordinate is x on the axis has coordinates x0. This point has coordinates x 1 over x squared. So we're going from point x0 to x 1 over x squared. We could use a Pythagorean theorem. You know, don't draw a fundamental triangle, but it would just be a straight line because you have the same x coordinate. So the length of the line from this to this, there's no change in x, but y changes from 0 to 1 over x squared. So the change in y is 1 over x squared. That's the length of that side. There are all kinds of ways to see it. Okay, so there it is. Then the question is, what's the length of the horizontal side along the x-axis? Well, the horizontal side, if we just look at this little schematic drawing that doesn't have all the complication of this one, I ask, what are the coordinates of this point here? Well, symmetry, well, the coordinates of the coordinates of this length, obviously the y-coordinate is 0 because it's on the x-axis, but the symmetry of this graph that you should have a pretty deep experience of tells us that the x-coordinate here is the negative of the x-coordinate here. Another way of looking at it is just that this distance has to equal this distance. So if this is x0, this has to be negative x0. So right there are the coordinates of the 2 points. And then the question is, how long is this side? Well, just from negative x to x, the distance from the origin to x, and this would be our y-axis, is just x. And the distance from negative x to the origin is just x. And you got x here, and you got x here, so the length of the side is 2x. Okay, now we've got that, we know what the dimensions of the rectangle are. Okay, it's 2x in this direction by 1 over x squared in this direction, the 1 over x squared we got here. What therefore is its area? Now, people actually had some hesitation on this. Took people a while to get this. Pretty quickly though, we got something about length times width, and that's right. Now, it's questionable which is the length and which is the width, but it doesn't matter. It's the length of one side times the length of one of the sides that's perpendicular to it. And I say that because if you used an x value here, you'd have an x value closer to 0, you'd have a rectangle that's longer this way than it is this way. Whereas this rectangle is longer this way than it is this way, at least the way I've drawn it. So you don't know which one's going to be the length and which one's going to be the width. That depends on the value you choose for x. For some values of x it'll be one way, for some values of x it'll be the other. But either way, if you multiply 2x by 1 over x squared, one of these is the length and one of them is the width. And it doesn't matter which, the area is going to be the same either way. If you multiply these then, you get 2 over x. And that's the area of the rectangle. Now, if we want to graph that function y equals 2 over x, which equals the area, well, here are the possible areas. Okay, the possible areas of the y-coordinates. We can see that there's no limit to how big the y-coordinate gets. Okay, if you pick x small enough, that's going to make this rectangle real narrow, but it's going to make it real high. And the rate at which it gets high exceeds the rate at which it gets narrow in such a way that the area is unbounded. Okay, there's no upper limit on the area that you can get from a rectangle using this graph. Okay, so as x goes to 0, as you move closer and closer here, this big long rectangle you get from here has an area that approaches infinity. There's no upper limit on the area you can get then by making narrow rectangles. Also, the lower limit is 0 because the graph is asymptotic to the x-axis. As x gets really large, this quotient gets really small, but it never actually approaches 0. So you can't get an area of 0, but if you let x get big enough, this function, which represents the area, it's not this function, this represents the area, gives you a result that approaches 0. So if you make very narrow rectangles, the area approaches infinity. If you make very wide rectangles, the area approaches 0. And this is really quite interesting. Okay, you follow the same procedures I used here, the same steps, with the graph that I kind of rubbed out here, the graph that's part of your assignment. And what you're going to get is not a multiple of the reciprocal function, the basic reciprocal function, which has unbounded areas, but in this case you're going to get a quadratic function that has a graph. Now that graph can't be expected to look like this graph, except it's the same general shape. It might open upwards. It's not going to have its vertex on the y-axis, but its vertex is going to tell you what the maximum or minimum area of the rectangle would be. So you can proceed if you follow the steps, and you should get a result that fits in with what you know about quadratic functions and the vertices and the way you get the maximum and the minimum by looking at the parabola.